Alright, so today we will be doing 6.3 notes for the first part of them, which is summation notation. So for summation notation, it's also sometimes called sigma notation because this fancy letter right here is a sigma. So that's your Greek letter for sigma. You'll see it on sororities and fraternities everywhere. It seems like it's a popular one. But it is also a mathematical symbol that we will use. So summation notation works like this. You've got your sigma, and then underneath it you're going to have usually they use I, although they could use a different letter. I, which is your index of summation, that's the number you start at. The number on top here, this N, that's your upper bound, and then you have some sort of expression. And summation notation is used whenever you need to add repeated values of a function. So we will do this first example here. Put them both up there. So, for this first equation, or expression that we have here, we have the sigma, which tells us we're taking the sum of I, and this will be from 1 to 6. So, what this will look like is you're going to take 1, you're going to plug it in for I right here, which in this case just gives you 1, right? And then you're going to do that with the next integer, so 2. Just plug it in for I, and we're going to add it to the 1 that we have. And then we'll plug in 3, and we'll plug in 4, and we'll plug in 5, and we'll plug in 6, and we will stop there because that is our upper bound for this summation. So if we have this notation right here, it just means that we need to do 1 plus 2 plus 3 plus 4 plus 5 plus 6. And so if we do that, we've got 6, 10, 21, I think, if we add that all together. Your calculator has summation notation on it. I think if you do F3, which is calc, and you go down to number 4, which is the sum, you will put in your equation, which I'm just going to call x. I'm going to use an x instead of an I think. I hope. And then I think you do comma 1, comma 6, and then close your parentheses. So you put your equation, 1, 6, close your parentheses, note. I might have to do another comma x. Let's see. I might have to look it up. Might have forgot. Okay. Alright, you have to do your equation. You have to do comma, whichever variable you're using. So like if I wanted to do it with i's, I could do it with i's. I just use x's because they're easy to type. But if you wanted to do it with i's, you could type I, comma, 1, comma 6, and you'll get 21. Now, this one, I think it's easier to do without using the summation on the calculator. And a lot of these they're not going to be calculator active, so you'll have to figure them out. but I did want to show you this because you are welcome to use it to check any of your answers on your homework. So it is helpful for that purpose. Okay, so this would be summation for example 1. Let's look at example 2. Example 2 is the sum of I plus 1 from 0 to 5. Okay, so the sum of I plus 1 from 0 to 5. So if you start at 0 here, you plug in 0 plus 1, and then you would plug in 1 plus 1, and 2 plus 1, 3 plus 1, 4 plus 1, and 5 plus 1. And so we would plug all of that in, which if you look at it, actually is 1 plus 2 plus 3 plus 4 plus 5 plus 6, which we just did, which is 21. Okay, so if we wanted to do that one in the calculator, we would choose number 4. We would do x plus 1. Oh wait, don't close that parentheses yet. Comma x, comma 0, comma 5. And you'll see we get the same answer there. Okay, questions? All right, let's do another one. So for this one, we've got the sum of from j equals 3 to 7 of j squared. So for this one, the first number we would plug in would be 3. So we have 3 squared plus 4 squared plus 5 squared plus 6 squared plus 7 squared. And so 9 plus 16 plus 25 plus 36 plus 49. And on your homework, it is okay with me for you to use the calculator after you get to this point, just because I don't want you to spend a lot of time just adding numbers together if they get kind of large. And it's fine if you want to use the summation to check your answer, but I do want you to write it out on those where you show how you've plugged those numbers in, unless it tells you to use the calculator. So you could use the calculator to add these numbers together. I'm typing them in wrong. I might be better off just doing it by hand. And we get 135 for that one. Okay, questions? All right, let's do another one. So, we're going to do this next one, and it's going to be a little bit different. So this one we will not get a number answer on because we're going from k equals 1 to n, so we won't get a number answer here. So we've got the sum from 1 to n of 1 over n times k squared plus 1. So k is our index of summation. We're going to start at 1. We're going to go to n, which we kind of can't do. But we are going to see a property here. We only replace the k with the number. So what this will look like is this. We'll have 1 over n times 1 squared plus 1. And then we'll have 1 over n times 2 squared plus 1. And 1 over n times 3 squared plus 1, and then 1 over n times 4 squared plus 1, and this is going on forever, and I'll put plus dot dot dot. I don't know what n is, but eventually I'm going to get to it, and I'll get 1 over n times n squared plus 1. So, I mostly gave you this to look at because I wanted you to see something here. When you have a different variable here, when you have an n on the inside here, and it's multiplied, it'd make a difference if it was added or subtracted. But if it's multiplied, then notice I've got a 1 over n with every single one of these. Even the ones in the middle that I've got the dot dot dots for, they'd all have 1 over n, right? So what can we do with that 1 over n? Factor it out front. So I could write it like this, 1 over n times, and then 1 squared plus 1 is 2, 2 squared plus 1 is 5, 3 squared plus 1 is 10, 17, dot, 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 n squared plus 1. Okay. You couldn't really go any further than this because this is the, we've still got that n in your expression, so you can't simplify it. I guess you could put 2, 5, 10, and 17 together, but that really doesn't do anything because you've got all those other numbers up to n, so you wouldn't really want to combine those. But the main reason I gave you this is because I wanted you to recognize a property. This 1 over n, because it's not the k, it can be pulled out front from the very beginning. So what we could have done here is we could have said this was 1 over n times the sum from k equals 1 to n of k squared plus 1. And so we could pull that out front, and then you would only have to work with this part right here. So this would be true no matter what value n is. Okay, now the reason that we are doing this is because we can use summation notation to express Riemann sums. So if we look, if you got x squared plus 5, that's a cubic, a quadratic that's been moved up 5. And let's do a right sum. Oh, do I really want to do a right sum? Yeah, we can do it. Right sum. Okay. So we would split this 1, 2, 3, 4, 5, 6 we would split this into 6 categories, and we would have the rectangles that looks like this. And I can't draw a whole picture because it didn't really make a lot of room there. But to do this by hand, before we knew anything about summation notation, we would just take the area of each rectangle. So it would be the width of the rectangle times the height. And so the width of the rectangle, what's the width of all of the rectangles? It is 1. So we could have 1 times, and then if we're doing our right sum, we need to use the right endpoint, so we will not use 0. We would use 1, 2, 3, 4, 5, and 6. So we would be finding f of 1 plus f of 2 plus f of 3 plus f of 4 plus f of 5 plus f of 6. And so we did that in our calculators already whenever we were doing our Riemann sums. And we just put y equals, we just put our equation in. We did y1 of 1, y1 of 2, y1 of 3, and so on, and added all those together. We could use summation notation instead, and it makes it a little bit easier to type in, at least. So what we're doing here is we're taking the sum. I'm going to go ahead and put this 1 right here. I'm going to put it on the outside. Now, I know technically you don't really need that 1 because you don't have to write times 1 whenever you multiply something by 1. But I'm putting it here because if that had been a 2 or a 3 or 4, you definitely have to have it. And so we're taking the equation x squared plus 5. And what is the first number that we plug in? 1. So x would equal 1, or we could use i's if we wanted, but we need these 2 letters to match. And where do we stop? What's the last number we plug in? 6. So instead of having to put this into y equals and do it that way, we could use summation notation. And so if we used our calculator for that, we could do the sum of x squared plus 5. Squared plus 5. And we do comma x so they know what variable was our summation variable. And then from, not 0, from 1 to 6. Okay, and that would give us 121. So that would be our right sum. Okay, so this expression gives you the right sum. What would give you the left sum? Okay, it'd still be 1 times the sum. It'd still be x squared plus 5. And we could change that x to 0. And instead of going from 1 to 6, we would go from 0 to 5. Right there. And if we did that, I just go over here and change my limits, we'd get 85. That would be your left sum. Okay. Questions? Mostly today we're just going to work with summation notation. I'm not going to have you doing this today. We are going to work on it eventually. But I just kind of wanted to show you this to show you where it plugs in. Because it seems like we're just doing crazy notation for no reason if we don't at least look at that a little bit. Alright, so let's look at this next example. So if we have to evaluate the sum from 1 to 3 of 5. This is a problem that is so easy that it is difficult, in my opinion, because I don't have a k right here to plug a number in. So for the first term, I would try to plug in a 1, but there's no k there, so I would just get 5 for my first term. And then what would I get when I try to plug in 2? I'd get 5 again. And then when I try to plug in 3, 5 again, right? And then I'm just going from 1 to 3, so I end up with 5 plus 5 plus 5, or I could do 5 times 3, which would give me 15. Okay, so there is a shortcut rule for this. If you are doing the sum from 1 to n of a constant, where c here is a constant, it's just going to be c times n. That's all you'll get. C has to be a constant. I must equal 1 in this case. So make sure you've got this written down. All right, let's come up with another shortcut rule. Okay, so I want a shortcut rule for the sum from I equals 1 to n of just I. So, I want to prove to you why the shortcut rule is what it is. So, we are going to do a rough proof here. If you were actually doing a mathematical proof, you would need to write out things a little bit more formally. But this is a mathematical proof. So, if I was doing I from 1 to n, that would be 1 plus 2 plus 3 plus dot 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 plus, I got to go to n. The last one's going to be n. The one before it would be n minus 1. Right? That would be the number that comes before n minus 1, or n, and then I'd have n. Actually, for the sake of the proof, leave that 3 right there off. It'll make our lives a little easier if it's not there. We could include it, but it'll be a little easier if it's not there. Okay, so this would be the sum of n. Alright, would it be okay if I wanted to, could I write it this way? N plus n minus 1 plus dot 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 plus 2 plus 1. Would it make any difference if I wrote it backwards like that? It should be the same, right? Oh, I forgot to put my I right here. Okay, and the reason I wrote it backwards is because what if I take these two expressions and I add them together? Okay, so if I add the sum from 1 to n of I plus the sum from 1 to n of I would get 2 times the sum from 1 to n of I. And I could add each one of my terms here. I'm adding these two expressions together. So right here, I'd get n plus 1. I do 1 plus n right here. Then I'd have 2 plus n minus 1. What would that give me? If I had 2 plus n minus 1, what would that be? That one's going to be n plus 1. Alright, I'm going to put my dot, dot, dots in the middle. What about n minus 1 plus 2? What's that give you? N plus 1. And the last one, n plus 1, gives us n plus 1. So what we've got right here is we've got that this 2 times the sum from 1 to n of I equals n plus 1 plus n plus 1 plus n plus 1 plus n plus 1 over and over and over again n times. And if we add something together n times, then we can write it like this. We could write this side like this. N times n plus 1. Right. If we had 5 3 times, 5 plus 5 plus 5, we could write that as 5 times 3. Right. If we had 7 4 times, 7 plus 7 plus 7 plus 7, we could write that as 7 times 4. So if we have n plus 1 n times, we can write it as n times n plus 1. And so 2 sum of 1 to n of I. 2 times the sum of 1 of I from 1 to n is going to equal n times n plus 1. So this is already sort of a shortcut rule for this, but most of the time...
Pardon interruption, just a reminder that at this time all girls who are interested in playing soccer this spring, please come to the media center. All girls interested in playing soccer, come to the media center. Thank you.
Soccer players. Okay. Are you not allowed to play this year? Alright. So you could divide both sides by 2. And so that would give us our shortcut rule. And our shortcut rule for this is that the sum from 1 to n of I equals n times n plus 1 over 2. Okay, so make sure you've got that shortcut rule down. So I will not ask you to do a proof of that, to go back through what we just did there. You do need to know that shortcut rule, and how to use it. But I kind of like to walk through it because it gives you sort of an understanding of why this is the case. So this shortcut rule here, we'll make sure we have it down. We could use it to evaluate this example here. I'll give you a second. 2 to 9 of I. We could do it the long way. Sometimes the long way is actually a little easier. The long way would be just like we were doing earlier. We could just do 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9. Depending on how large your numbers are, it's not all that bad to do. You're going to get 45 whenever you do that. Or we could use our new shortcut rule. And our new shortcut rule tells us that we would take n, which n is our 9 right here, and we would do 9 times 9 plus 1 divided by 2. And so that would be 9 times 10 divided by 2, which would be 90, divided by 2, which would give us 45 also. Questions? Okay, we've got a couple more shortcut rules. I will not make you go through the proofs of them for a couple reasons. Number one, I don't know how to do them. Number two, they would take forever. I'm sure I could figure it out, but I have not yet decided that it's worth my time to do that. So here are our other two shortcut rules. So copy these down. 10 of I plus 1 over n squared. So the n is 10. So I could do this. I could go ahead and plug in that 10. And that would give me the sum from 1 to 10 of I plus 1 over 100. And since this is just a constant, I could pull it out front. It still has to be in the denominator, so it would be 1 over 100 times the sum from 1 to 10 of I plus 1. So the first thing I did here, I would do the same whether I were doing the easier way or the, I'm not going to call it the easy way, the long way or the shortcut way, is I would get that any coefficients that you can pull out because they go with everything, you want to pull that out so that you don't have to do it every time. So this 1 over 100, I would pull that out. Then you still have the option of doing this the long way. If you do this the long way, you've got 1 over 100 times 1 plus 1 plus 2 plus 1 plus 3 plus 1 plus, I'm going to put a dot, 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 plus 10 plus 1, which would be 1 over 100 times 2 plus 3 plus 4 plus dot, 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 all the way to 11. And so it's pretty simple to do this one, especially if you grab your calculator. These would be expected to be done non-calculator, but I don't mind you using the calculator to add up 2, 3, 4 through 11 just to speed you up a little bit. And you get 13 over 20 because I think this is going to be 65. I think you get 65 over 100 whenever you do this, which reduces to 13 over 20, I believe. So that would be just writing it out like we've been doing from the beginning. If you have smaller numbers, it's really not all that bad to do. But let's also use the shortcut method. Okay, so if we go back to what we had here, the 1 over 100 times the sum from 1 to 10 of I plus 1. So what we would do here is we'd still have 1 over 100, and we could break these two right here apart. We could do the sum from 1 to 10 of I plus the sum from 1 to 10 of 1. So you're just taking the sum of those two things separately. And our shortcut told us that if we are taking the sum of I, then we would have n times n plus 1 over 2. So 10 times 10 plus 1 over 2. And our shortcut for the sum of a constant is just n times that constant. So 10 times 1. And so right here we get 10 times 11, so we get 110 over 2 plus 10. Which is going to give us 55 plus 10, and here is our 65 over 100, which is going to give us 13 over 20. Now, you probably are looking at this and saying, Ms. Hyatt, your shortcut way looks a little longer than your long way. Sometimes that's the case. I have to teach you these shortcuts, though, because there's a step we're going to get to where the shortcuts have to be used. Whenever you get to some of these, do try to use those shortcuts, even though it might be quicker at times to use the longer way. Okay, questions? Okay, so here is one where, especially if it's technically calculator inactive, it starts to become worth it not to use the long way. Because for this one, you're going from 1 to 15. So first off, you've got 15 terms you got to add together, and you've got to do I squared minus 1. So that is going to make this a little bit lengthy, and it's going to start to make it worth it just to use your shortcut method. So first of all, this n right here is 15. So I'm going to replace that 15. So I'd have 1 to 15 of 15 times I squared minus 1. And this 15 we can pull out front. So we want to do that. 15 times the sum from 1 to 15 of I squared minus 1. Okay, so we're going to use our shortcuts here. We'll have the 15. It'll just kind of stay out front. I squared, the shortcut for it is n times n plus 1 times 2n plus 1 over 6. So I will say 15 times 15 plus 1 times 2 times 15 plus 1 all over 6 for the I squared. Minus, this is just a constant, so I'm going to do 1 times 15. And so that's going to give me 15 times 16 times 31 all over 6. For the sake of you not having to spend the rest of your life doing this homework assignment, I don't mind if you use the calculator for these last steps. So you get 15 times 450, and so you would get 6. Oh, wait, I messed up. 15, 16, 31. Let's see. Oh, I divided by 16 right here. Let me try it again. 7440 divided by 6. Alright, that should be 1240 minus 15, which is 1225. Which is going to give you 18,375. Okay, questions? Alright, I've got one more thing that we need to do. I'm going to give you a second to copy these down, and then we're going to write these expressions with sigma notation. 4 is a number that is increasing by 1, or there will be I don't think we'll get into the more difficult ones where they're odd numbers or even numbers, but like here clearly we see this is just 1, 2, 3, 4, 5, 6, 7, right? So we're just increasing by 1 there. So this one, we're going to have summation notation. I equals 1. We start at 1. We go up to 7. We're just using the number, just I, right? And so it will be the sum from 1 to 7 of I. For that one. So whatever value is increasing by 1 each time, that is your I. So if we look at B, we've got 4 squared plus 1 plus 5 squared plus 1 plus dot dot dot, and then 9 squared plus 1. So 4, 5, 6, 7, 8, 9. Right? This number right here is the one that's changing. So that is our I. So when we do our summation, it's going to be of I squared plus 1. So whatever number is changing, you can just change it to your I. What would our I begin at? It would start at 4. What would it go to? 9. Now, when you get down to C, I think it is kind of difficult. What number's changing? The one over the end. So you go from 1, 2, none of the middle ones are listed, 3, 4, 5, 6, 7, 8, all the way up to N. Okay, so we are doing the sum of, and we can say 1 over N times 6 plus I over N. And that I began at 1. What does it go up to? N. There. Now, they can make this even difficult if they reduce that N over N to 1. So you just have 6 times 7, or 1 over N times 7 there, which would make it more difficult to figure out the pattern, I think. For that one. Okay. Also, it would be perfectly fine if you took this 1 over N and pulled it out front. So 1 over N times the sum of 1 to N of 6 plus I over N. That would be fine also. You cannot pull this N out because it's added to that 6. It has to be a coefficient that's multiplied, but you could pull the 1 over N out. Okay, and then the last one, what number is changing? The 1 over the N squared this time. That number is changing each time. So we would say, I'm going to go ahead this time, I'm going to write that N out front. The sum from 1 to N of the square root of 1 plus I over N squared. Okay, questions? Okay, so your assignment is going to be on page, make sure that's right. 299, numbers 1 through 20. Okay, just like I've done here, you're welcome to use your calculator after you've written out how you're going to do it to get those numbers so that you don't have to spend all day just adding, subtracting, multiplying, and dividing. And you're also welcome to use the summation notation to check your answers, especially on those even problems where you don't have them. So go ahead and get started. You got about 25 minutes. You might be able to get a lot of this done before you go.